So we've been going through our physical science section, which would be essentially chemistry and physics. So we are moving through chemistry and now getting more to the physics side of things. Today we're going to talk about a little bit about energy, and we'll probably spend a couple days talking about energy because it's a big and can be a broad topic. So I apologize for just kind of spitting everything out and kind of giving you a bunch of stuff to look at. I know it's not as interactive or exciting as I would like it to be. Keep working on things and hopefully continue to improve classes as this kind of goes on. So when we're talking about energy, in a broad sense, right? Like when we think of energy, we might think of electricity, or we might think of being tired or lacking energy, physically in our bodies, and those are all examples of it. When we're talking about energy in science, we're talking about a big idea. And energy, most simply put, is just the capacity to do work. And so what I mean by that is moving stuff around. What I mean by that is anything that has the ability to do something or to do work, we would say contains energy or is considered energy, right? And so and I'm just going to kind of run through these terms, and I know they're up there and you can kind of look at them. Energy is the capacity to do work. And what is work? And again, we're looking at this just from a science point of view, not necessarily like we're familiar with the word work, right? You might consider that to be a job, or doing homework, or physically working on something, right? That's all work. But again, in kind of the broad sense of the term as I'm using it here, work is done whenever a force is applied to an object to set it in motion. Okay? So going back to energy, energy isn't necessarily actively doing work, right? Notice when it says what energy is, it just says the capacity to do work. So energy can take the form of something that's not actively doing anything. We're going to talk about that a little bit later today. Energy can be actively doing work, or it could just be the fact that something has the ability or the capacity to do that. So a couple other terms, and then we'll go ahead and get started. Talking about kind of the main concept of the day, which is going to be this part down here. I'm pointing at my screen, but realize you can't see it. Kinetic versus potential. So that's going to be what we spend the bulk of the day on. The last kind of term I want to go over would be power. And so power is simply the rate of doing work or consuming. And so think about running versus walking. Right? Both of those things require energy. One of them is using energy at a much greater rate, right? To run requires much more energy than to walk. So in theory, we can walk for a lot longer because we're using our energy more slowly. Whereas to run, right, we're going to expel or to run out of energy a lot faster, right? So power is simply the rate of either doing work or consuming energy. So I'll come back to those terms every now and then, but just so you have a very clear idea of what energy, work, and power are, that will go along there. So the other kind of term or kind of vocabulary thing I want to go over, which actually isn't up here on this slide, but is the law of conservation of energy. And so if I skip forward, I kind of skip ahead more than I typically do. So just kind of ignore this other stuff. We're going to talk about this probably tomorrow, but I bring this up just simply because of this part down here at the very bottom. where it says energy can be converted from one form to another, but energy cannot be created or destroyed. That is the law of conservation. So similar to what we talked about with, you were in class or you saw yesterday's video, good, because actually the recording didn't work, but we talked about chemical reactions and chemical equations, and we talked about the law of conservation of mass, which basically says when a chemical reaction occurs, you have to have an equal amount of mass at the beginning as you do at the end. And the same goes for energy. Okay, so energy cannot be created or destroyed. It can only change form, right? So in other words, if I turn the light switch off, I'm not destroying energy, right? The energy is just taken a different form, but I can go and easily put the light switch back on, and the lights come back on, and I didn't create energy, right? That energy just went somewhere, was stored, and was waiting for me to switch on, and when it turned on, it changed form again and came back on, right? But it didn't actually go away, and it didn't actually magically come back. So that's the point I'm going to talk about. All right. So back to what I was. Let me get back to where I was, which was right here. Okay. So, like I had said earlier, this is kind of where I want to spend the bulk of the day talking about, which is the difference between potential and kinetic energy. This is going to be one of those lessons where I'm going to try my best, but usually it's easier if I can draw lots of stuff, and I might utilize the whiteboard if I feel the need to kind of illustrate my point. But I'm going to try my best to keep it as simple as possible. So energy exists in a lot of different forms, and there are lots of different types of energy, and we're going to get into the types of energy more tomorrow. Today, I just want to look at the main difference between kinetic energy. So first, kinetic energy. So kinetic energy, and you can see the definition. Kinetic energy is the energy in an object's motion. So in other words, kinetic energy is only being generated when something is moving, right? Actively moving. And that depends on a couple things. In other words, there are a couple factors that go into determining the amount of kinetic energy something has. And you can see down here, right, it says kinetic energy depends on mass and how fast the object is moving, okay? So if I take, so pardon my lack of good examples, right, but I have, in one hand I've got a big GED, right, so over here I've got this book. Over here in my other hand I have a calculator, right? Both of these objects have mass. What has more mass? The book has much more mass than the calculator. So if I were to throw these things against my computer, I'm not going to do it, right? Which is going to hit the computer with more force, assuming I throw them at equal speed or velocity, right? The book's obviously going in, knock my computer over, whereas the calculator might ding the screen or something. So if we're talking about kinetic energy, if velocity or speed is constant, meaning the same, obviously this book is going to be traveling with much more kinetic energy than the calculator. So you can see down here the formula for kinetic energy. Memorizing the formula is not essential for our purposes. Kinetic energy is 1/2 times the mass times the velocity squared. Right? And that gives you a number or how much kinetic energy something has. But if you just, all I really want you to remember is kinetic energy is energy of an object's motion, and it's dependent on the mass that object has and how fast it's traveling. And I want you to just kind of leave it at that. All right? So you can see down here, the last little thing says, if two objects have equal mass, then the object that is moving faster has more kinetic energy. So by the same logic of my earlier example, where if these two objects are traveling the same speed, And the one with more mass obviously has more kinetic energy. But let's assume, and this is a phone, but let's assume that these two things are equal. They're not, but just for the sake of this example, consider there two calculators, identical mass. Obviously, if I throw one faster than the other, and this one's traveling slow and this one's traveling fast, obviously the one that's traveling faster is generating more kinetic energy. That's all there is to it. Okay? And now let's talk about potential energy. And I'll give a little example and a little diagram that might explain the relationship between the two a little bit. So potential energy is simply the energy due to an object's position. Okay? So what the heck do we mean by it? So think of the word potential. Potential, if I say a student has a lot of potential, that means they might be very smart, they might have great work ethic, they might be extremely talented in something, but it doesn't mean that they're actively utilizing those skills. It just means that they might, or that they could. Same thing with energy. Potential energy doesn't have anything to do with how fast something's traveling or the active energy something has. Potential energy just says, how much energy could this object have, right? And so if we look at the, down here on the very bottom, the equation. I lost track of my thoughts for a minute, right? But the equation down here for potential energy, again, remember, I don't need you to memorize equations, but the formula for potential energy is mass times gravitational pull times height. So for the sake of this experiment and this discussion, let's just assume we're on Earth. Gravity is always the same on Earth. So let's take that factor out and just think of the two factors that go into potential energy, where, as opposed to kinetic, where the two factors are mass, how big, dense something is, versus how fast something's traveling. Potential energy is also mass, but velocity or speed or motion isn't the other factor. The other factor with potential energy is height. Think about that, right? Let's take my two bad examples here, the calculator and the book. If I set these two things down on the ground, they have no potential energy. They're not going to generate any energy on their own. But if I hold both of these way up high, right, then now I've given these two objects potential energy. Because think about if I was to drop these two things, now all of a sudden they took that potential energy and they turned it into kinetic energy. And they both reached the floor and they both hit with a certain amount of force based on how big it was and how high it was. So again, if I want to increase something's potential energy, there's a couple things I can do. I can increase the mass, hit a bigger object. So these two objects, they are at the same height. Obviously, the one with more mass is going to have more potential energy. But I can also increase the height. Right? I can increase something's height. So if I take this calculator and I put it on the roof of the building, all of a sudden now, this calculator may have a lot more potential energy than the book if I hold the book up a couple feet off the ground. This calculator is up 40 feet. And think about it this way. I try to explain energy, both potential and kinetic, as thinking about what it would feel like for those objects to hit. Because if something hurts more when it hits you, because it's hitting you with more energy. So if I take the calculator and I pick it up on the roof of the building and drop it on you, it's going to hurt like hell if it hits you on the head. But if I take the book and just drop it, 1 foot off the ground and it lands on your foot, it might not feel good, but it's not going to hurt a lot. But I take that same book and I hoist it up off the roof and it hits you down. It's going to hit with a lot of force. It's probably going to hurt you, injure you. So think about energy that way, and maybe it will drive the point home more uh, of whether something has a lot of energy versus more or less. Well, enough of me rambling on, dropping books and calculators. Let me pull up the image I was talking about and explain potential and kinetic energy in a little different way, and then we'll do a practice question to kind of end the day. So let me hopefully you can see this. If you can't, then let me know in the chat. But hopefully you can see this picture here. It's like a pendulum. So imagine, so I know that there's 5 dots on this pendulum, but really imagine we've got, going back and forth and back. That's what this picture is essentially showing. Okay? So at each point, at each endpoint of a swing, so if you're on a swing, right, so you're here, you go down and back up, and you stop, and you go back down and back up the other way. At these 2 endpoints, think about what you're doing. You're sitting on a swing. This exact point here and this exact point here, you're not moving at all. You're stopping and you're changing direction. Okay? You might not think of it in terms of that because it's so fast. But for you to turn around and change directions, you have to, for a split second, stop. Okay? So at that moment, when you're stopped, if you look here on the picture, so that's this point here, this point, both ends. You have no kinetic energy because you're not moving. Remember, kinetic energy is the energy of an object's motion. Energy of an object's motion. So if you're not moving, then you're not generating kinetic energy. So at this point and this point on the sides, notice how it says kinetic energy equals 0. That's what I'm talking about. But remember the factors that go into potential energy, which are mass, and assuming you're the same person on the swing, the mass isn't changing. We're taking mass out of it, and we're just looking at the variables of velocity or speed and height. So at those endpoints, our kinetic energy is 0 because we're not moving. But our potential energy, think about where we are height-wise. If we're on a swing, and we start here and we swing down and we swing up and we swing down and we swing up, relative to the ground, our height is never going to be greater than it is at those endpoints. Our height is at 100% essentially. Doesn't matter how big or small the swing is, relative to our swing, these are the 2 heights. Would you agree? Hopefully you're nodding and saying you get it. Not, then we can talk about that. But remember, if height is the factor in potential energy, then at these 2 points, potential energy is at its maximum, which is what it says, right? PE equals max, KE equals 0. So kinetic energy and potential energy are inverses of each other. In other words, if we have none of one, then we should have a maximum of the other. Okay, so potential energy is at max here and here. Kinetic energy is at 0. Once we start moving, right? Once we start swinging down, what happens to our velocity? We slowly start to increase our speed, right? So we're swinging. Now we're getting faster and faster and faster and faster and faster and faster until that low point. Now in reality and theory, this low point should be where we're traveling fastest because our speed is increasing as we're coming down. Then the moment we start to go up, we start to slow down. So by that logic, our kinetic energy is maximized at that low point. In other words, we're never going to be generating as much kinetic energy or traveling as fast as we are at that low point. From that point up, we're going to start to lose kinetic energy. And from this point down, our kinetic energy is going to increase. Maximum, and then decrease, 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 back to zero. If that makes sense, right? Now, let's look at the points in between. So obviously, if we start on the end and we lose height, but gain velocity, we're gaining kinetic energy. In other words, our kinetic energy is going up because we're going faster, but we're losing potential energy because we're losing height. We have less and less potential to gain energy, and we're transferring more and more of that energy into actual kinetic energy, moving faster. Once we reach the bottom, now we pass this point here, where there's a split second where even though our energies are going in opposite directions, in other words, we're losing kinetic energy, gaining potential energy, losing potential energy, but we're gaining kinetic energy. At one point, the two hit an equilibrium, right? Where we had exactly the same amount of potential energy. Then as we continue down, we keep losing potential energy and gaining kinetic energy until we get to here. Potential energy is at zero, kinetic energy is maximized. As we go up, we start to gain height, so we start to gain potential energy, but we start to lose velocity, so we're losing kinetic energy. So the energy isn't really, when I say gaining and losing, the amount of energy generated by you on the swing isn't going up and down. Remember, we talked about this earlier. It's just being transferred into a different form of energy. But the amount of energy involved in this whole example is the same. It's just a matter of whether it's potential energy, kinetic energy, or some combination of the two. That kind of makes sense. So we've got about 5 minutes. So I want to look at one question, and we may end up just being a little bit early today, but I don't want to get beyond this, I think. So I think for the sake of keeping things kind of on one topic, we'll do a question, and then if anyone has any questions, we can ask or we can answer them, and then we'll just call it. So I'm going to close out of this. All right. So these questions here, there's a couple questions that go over some stuff we haven't talked about, so we're going to do those tomorrow. We're going to start with number 1, and then we're going to do number 5. So we're just going to do these 2 questions. And feel free to, if you want, you don't have to, but if you want to answer these questions in the chat, definitely feel free to. If you don't, that's okay. If you want to respond either to Caleb or myself privately in the chat, just to make sure you're getting it, that's okay too, so that other people don't see it. Just putting it out there so we can try to interact as much as possible. Let's look at number 1 here. Number 1 says, which of the following states the law of conservation of energy? Remember earlier what we talked about. A, potential energy is the energy of motion. Kinetic energy, I'm just messing my words up today. A says potential energy is the energy of position. Kinetic energy is the energy of motion. So A, that's a true statement, right? We talked about that, and that is what potential energy is, and that is what kinetic. The difference is that doesn't state what the law of conservation of energy is. So when we're talking about practice questions, that's something that you always expect to see. You'll see statements that are true, that are accurate, but they don't answer the question. Be careful for that. So A is not the right answer. B, energy can be created and destroyed as well as changed in form. So let's look at B, C, and D, because B, C, and D are all worded similarly, but kind of mixed around. So B, energy can be created or destroyed as well as changed in form. C, energy cannot be created or destroyed, but can only change in form. Or D, energy cannot be created, destroyed, or changed. So the first key difference is B says energy can be created or destroyed. C and D both say energy cannot. And if you remember from earlier, we talked about energy. The one thing we know about energy is it cannot be created or destroyed. Remember, me turning the light off doesn't destroy energy. It just stores it differently. And then when I turn the light back on, that energy then turns into a different form of energy. But I haven't destroyed or created any energy. It's just shifted. So I kind of, by describing that, answered the question for us. So if A is wrong, and we know B is wrong because energy cannot be created or destroyed, between C and D, the only difference is in this last part. C says energy can change in form, and D says energy cannot be changed in form. And we know from what I was just saying that even though you can't create or destroy energy, you can change its form, right? So when I turn the light switch off, I essentially, we've gone from light energy or kinetic energy, active, like we can see the light. When I cut the light switch off, it's changed form. It's now stored up as potential energy, but it's still there. And then when I turn the light back on, it releases the light again, and we can see the light again. So it can change form. It just can't be created or destroyed. So C is the right answer there. All right, and then real quickly, I'll try not to over-explain, which I know is one of my downfalls. I like to try to sit and talk things through, and I end up boring everyone. Last question. Again, this looks similar to what we talked about with the swing example. So the graphic here says pendulum's energy, and we have 1, 2, and 3. 1 says pendulum has only potential energy. 2 says pendulum has only kinetic energy. And 3 says pendulum has only potential energy. I'm not going to go over that again because we spent a few minutes talking. And number 5 says, based on that graphic, number 5 says, which of the following statements is supported by the information in the middle? So let's look at our options. A, at the high point of its swing, pendulum has kinetic energy. B, at the high point of its swing, pendulum has potential energy. C, as a pendulum swings through one arc, it loses all its energy. And D, a pendulum can swing forever because of kinetic energy. All right, so let's look into which of these is supported by just the information we see. Again, take away anything that can't be directly proven based on this graph. Okay? So for me, the first two, and feel free to answer on your own, but I'm just going to talk us through it. We're kind of running short on time. C and D would be the first two that I'd throw away. Because whether or not C is true or D is true, or neither of them, is a moot point. Because nothing in this graph tells us anything about the amount of swing. So C, as a pendulum swings through one arc, it loses all of its energy. It's a false statement, it's not true, but even if it was true, we can't prove it by the information they give us. Same thing with D. Pendulum can swing forever because of kinetic energy. We have no basis to prove whether or not that's true just based on the information they gave us. So throw it away. Don't make assumptions that we can't directly prove based on the information they give us. So we know the answer is either going to be A or B. Both of them are similar, except for A says at the high point, remember at the two sides, a pendulum has kinetic energy. B says at the high point of a swing, a pendulum has potential energy. Remember, at that high point here and at the high point here, you're not moving. Your height is as high as it's going to be. So you have potential energy or kinetic energy. You have potential energy. So there's your answer. So B would be the correct answer. All right, with that said, if nobody has any questions, we'll go ahead and stop for the day. And tomorrow we will finish up talking about energy and moving on through physics.